In the semiconductor world, it's not always the strongest material that wins the market. It's the material you can actually make at scale. AlN is a material with extraordinary performance on paper, yet for over 30 years it has been held back by a single problem. We can't make the substrate. I see today's achievement from Tohoku University as research that is trying to crack open that door.
Hello everyone, I'm Ty with 31 years in the semiconductor industry. As always, I'll explain everything in the most simplified way possible. Even a middle schooler should be able to follow along. If you're a specialist watching, some parts may feel oversimplified, but I'd like to prioritize giving everyone the big picture first. Think of it like a legendary mountain clay that fires into perfect pottery, but no one has ever been able to gather more than a spoonful of it. So sit back and enjoy. Here's an analogy to frame today's news. Deep in a remote mountain range, there's said to be a legendary clay. When fired in a kiln, it produces pottery of breathtaking beauty, extraordinary durability, and remarkable heat resistance. Every master potter in the world would give anything to get their hands on it. But there's a catch. This clay is scattered in tiny pockets throughout the mountains, and the most you can ever gather at one time is about a spoonful. You can make a prototype or two, but producing enough to actually sell? Completely out of the question. For decades, potters racked their brains over this. Could they recreate this clay artificially? Could they grow more of it somewhere else? But the crystal structure of this clay is so unique that even the slightest deviation in conditions produces something entirely different. Whenever anyone tried to produce it in large quantities, the very quality that made it special, that mysterious strength and beauty, simply vanished. The one non-negotiable prerequisite for everything else was finding a single, small, high-quality fragment to use as a seed.
Recently, a research team found a breakthrough. By combining a specific temperature range with a precisely controlled gas environment, they managed to grow this legendary clay into long, needle-shaped crystals. What had previously come out riddled with impurities could now be extracted as remarkably uniform needles, a few centimeters long and roughly 0.3 millimeters thick, about the width of 3 or 4 human hairs. The quantity is still small, but for the first time, a high-quality seed was finally in their hands.
What's even more remarkable is the next step. They used those needle-shaped crystals as seeds and attempted to grow them into something larger. They submerged the seeds in a special liquid and carefully controlled the conditions to let the crystal grow slowly and steadily. The result? A growth rate of 175 micrometers per hour, meaning the crystal expanded by 0.175 millimeters every single hour in a clean, uniform fashion. For the first time, a clear path toward growing the seed into something bigger had come into view.
Of course, this stage is still at the level of, we've established a seed and a growth method in the laboratory. This doesn't translate directly into mass production. But going from a state where we couldn't even get a seed for decades to we now have high-quality seeds and a preliminary roadmap for growing them is undeniably a meaningful step forward. From here, let me walk you through how this analogy maps onto what's actually happening in the semiconductor industry, in concrete technical detail. Let me get into the full technical breakdown. The Tohoku University Research Group announced that they successfully grew single-crystal AlN, aluminum nitride, using a direct nitration method. They produced needle-shaped AlN single crystals several centimeters long and up to 300 micrometers in diameter. By then using these as seed crystals in a solution growth method, they achieved a growth rate of 175 micrometers per hour. So why is AlN attracting so much attention? Let me start with the basics. AlN has a bandgap of approximately 6.2 eV, electron volts. Compare that to SiC at roughly 3.3 eV and GaN at roughly 3.4 eV, and you'll see that AlN has about 1.8 to 1.9 times the bandgap of those materials. The wider the bandgap, the better a material can withstand harsh operating conditions, like high voltage and high temperature. In theory, AlN is one of the top candidates as a substrate material for next-generation power semiconductors, as well as for deep UV LEDs,
devices that emit light in the 200 to 280 nanometer wavelength range.
Yet, AlN has been plagued for years by the problem of we can't make a substrate. To produce a single crystal substrate, you first need a large, high-quality single crystal boule. Even GaN still faces challenges in growing large-scale bulk crystals, and most commercial products use a method where a GaN thin film is deposited on a sapphire or silicon carbide substrate. AlN is even harder than that. It has an extremely high melting point and high vapor pressure, making it prone to impurity contamination with conventional growth methods. Obtaining large, low-defect single crystals has been extraordinarily difficult.
The key to Tohoku University's approach is a two-stage process. First, they use direct nitridation to create the seed crystal. This involves melting an iron-aluminum alloy, then reacting the aluminum vapor it releases with nitrogen gas to form AlN. The critical innovation was controlling the driving force of this reaction to just barely above the thermodynamic equilibrium point, keeping it extremely gentle. By deliberately slowing the reaction down, they suppressed the formation of excess crystal nuclei. What previously would have resulted in scattered polycrystals or nanowires could instead be extracted as needle-shaped single crystals several centimeters long and up to 300 micrometers in diameter.
The next step, using those seed crystals, is solution growth. This involves placing the seed crystal into a solvent, specifically a flux made of iron and chromium, and slowly growing the crystal under carefully controlled temperature and other conditions. In this experiment, they achieved a growth rate of 175 micrometers per hour. That number might sound small in isolation, but achieving this rate with AlN solution growth carries significant scientific weight. For the first time, the team simultaneously demonstrated two things as a paired result. We can produce a seed, and we have a method to grow it.
This brings to mind the history of silicon carbide and gallium nitride. Silicon carbide was also long described as the theoretically strongest material, yet it took decades before a practical substrate could actually be produced. Its potential was recognized in the 1970s and 80s, but commercial silicon carbide wafers didn't appear until the 1990s, and widespread adoption in electric vehicles has only accelerated over the last decade or so. Gallium nitride followed a similar trajectory. My honest read is that AlN is now arriving at the very same first entrance that silicon carbide and gallium nitride once had to pass through.
It's not the strongest material. It's the material you can actually make that wins the market. This is a truth that has been proven over and over again in the world of semiconductor materials. AlN's theoretical numbers are superior to any existing substrate material on paper. But the real question is, can you supply it at the size, quality, and cost required to use it as a substrate? Today's Tohoku University result represents the entrance to that entrance. And yet, the history of SiC and GaN also reminds us just how difficult it is to even reach that entrance in the first place. Looking at the current deep UV LED market, the mainstream approach uses thin film structures made of AlGaN, aluminum gallium nitride. If AlN single crystal substrates became available, lattice constant matching would improve, and device efficiency gains would follow. But currently, almost all production relies on depositing AlGaN thin films onto sapphire substrates. If AlN bulk substrates became widely available, this entire market could be transformed, but that requires actually realizing AlN substrates that can be mass-produced. Let me also put into context what's expected of AlN in the power semiconductor space. AlN is sometimes listed alongside silicon carbide, gallium nitride, gallium oxide, Ga2O3, and diamond as a candidate material for next-generation power semiconductors. AlN's theoretical performance is strong thanks to its combination of high breakdown electric field and favorable thermal conductivity, but the difficulty of actually fabricating devices from it is also a step above the rest. Even within the research and development phase at this point in time, the field is still at the stage where crystal growth technology itself is the core bottleneck. The most accurate description is that AlN is now arriving at the same stage silicon carbide reached in the 1990s. Let me take a closer look at the direct nitridation technique that underpins this research. The conventional mainstream approach for AlN bulk crystal growth has been sublimation, the PVT method, also used for SiC,
a high-temperature vapor phase technique. The new approach here takes a fundamentally different philosophy, gently nitridating aluminum vapor near thermodynamic equilibrium, contrasting sharply with the high driving forces used in conventional methods. This two-stage strategy, vapor phase seed creation followed by solution growth, represents one potential answer to the long-standing challenge of stably supplying high-quality seed crystals. That said, the current diameter of 300 micrometers is still 2 to 3 orders of magnitude away from the 100 millimeter plus wafer diameter that practical commercial use would require, a gap of hundreds of times.
So what comes next? Realistically, the immediate next hurdle is whether they can reproducibly grow bulk crystals in the range of a few millimeters to a few centimeters in diameter. Only after clearing that bar can the field move to the step of slicing them into wafers. In the case of SiC, the first commercial wafers started at around 1 inch, 25 millimeter diameter, and have since progressed to 150 to 200 millimeters today. AlN has more challenging material properties than SiC, so this road is likely to be even longer. Nevertheless, today's research, which demonstrated progress on both seed crystal quality and solution growth rate, will be recorded as the first milestone on that long journey. That is how I see it. Let me pull together everything we've covered. AlN is a material with theoretically top-class performance as a substrate for deep UV LEDs and next-generation power semiconductors. Yet for over 30 years, it has been stalled by the single problem of we cannot produce large, low-defect single-crystal substrates. Today's Tohoku University result involves growing high-quality needle-shaped seed crystals via direct nitridation and achieving a growth rate of 175 micrometers per hour using those seeds in solution growth. The challenge facing AlN is not the material's performance, it is establishing the substrate manufacturing method. Today's work has provided an important clue at that entrance. Mapping this onto the histories of SiC and GaN, the road to commercial substrates is still expected to be long, but seeds are now obtainable and a path for growing them has come into view is undeniably meaningful progress.
Let me wrap up. What makes today's research impressive is not we discovered that AlN is a great material. We've known that for a long time. What's impressive is that the team simultaneously demonstrated both how to produce high-quality seed crystals and how to grow them as a package. In the semiconductor materials world, theoretical performance doesn't decide everything. What decides everything is, can you make it? SiC and GaN each took more than 20 years to clear that can you make it barrier. AlN is now at the stage of knocking on that very first door. This isn't a flashy mass production announcement, but this kind of fundamental technical progress is what reshapes entire industries 10 and 20 years down the road. It may not make big headlines, but this is research you should not take your eyes off.
That's all for today. I'll keep bringing you semiconductor news and analysis. So if you found this useful, please like, subscribe, and I'll see you in the next video. This has been Ty on Semiconductor News Decoded.